All right, Algebra 1. We've been talking a lot about functions, which we call f of x equals something, 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 something. Today, we are actually going to transition that into graphing the equation of y equals f of x. We graph y equals f of x because our graph has a y-axis and an x-axis, not an f of x axis. So in Module 1, you graphed equations such as 4x plus y equals 10 by plotting the points on the Cartesian coordinate plane that corresponded to all of the ordered pairs of numbers xy that were in the solution set. We called the geometric figure that resulted from plotting those points in the plane the graph of the equation in two variables. In this lesson, we extend this notion of the graph of an equation to the graph of y equals f of x for a function f. In doing so, we use computer thought code to describe the process of generating the ordered pairs in the graph of y equals f of x. So, our first example, in the previous lesson we studied a simple type of instruction that computers perform called a for and x loop. Most of you understand what a for and x loop is. Another simple type of instruction is an if-then statement. Even if you don't understand computers, if-then statements are pretty common. Below is an example of example code of a program that tests for and prints true when x plus 2 equals 4. Otherwise, it prints false. So declare x an integer. We remember what an integer is. It's whole numbers for all x from 1 to 4. So that means we're going to test 1, 2, 3, and 4. If x plus 2 equals 4, then print true, else print false. And if, next x. So this loop is going to go through. It's going to test 1. If 1 plus 2 equals 4, then print true, else print false. End, and then try the next one. It's going to try 2. If 2 plus 2 equals 4, then print true, else print false. And if, next x, try the next one. Okay, it's going to go through each one of these integers from 1 to 4. And of course, for 1 it prints false, for 2 it prints true, for 3 false, for 4 false. Notice that the if-then statement in the code above is really just testing whether each number in the loop is in the solution set. Is it a true statement? Does it make an answer? All right, let's try another one. Perform the instructions of the following programming code as if you were a computer and your paper were the computer screen. So first of all, declare x an integer. Initialize g as an empty set. For all x from 0 to 4, and if x is an integer for all x from 0 to 4, that means we're going to test 0, 1, 2, 3, and 4. If x squared minus 4x plus 5 equals 2, then append x to g. Remember, this word append means add. Add x to the set g, else do not append x to g. And if, next f, next x, print g. So the computer is going to test each one of these integers in this equation, and if it makes a true statement, we're going to add it to the currently empty set of g. If it doesn't, it's not going to do anything. It's going to end its program and start again. Cool? So the only thing that it found true were the outputs, or the integers 1 and 3. And if I test that, I've got 1 squared minus 4 plus 5 equals 2. So 1 minus 4 plus 5 is negative 3 plus 5. 2 equals 2 is a true statement. And then 3. 3 squared is 9, minus 4 times 3 is 12, plus 5 equals 2. 9 minus 12 is negative 3 plus 5, 2 equals 2. So those were both true. So this if statement was true, so it added that integer to my empty set of G. All right. So compare the for next if then code to the following set builder notation we used to describe the solution sets in Module 1. If we read this, which we have to understand how to read it, we're going to say the set x is an integer such that x is between 0 and 4 and x is a part of this equation. It makes this equation true. So x is an integer between 0 and 4 and makes the statement true. This is set builder notation. So the set of all x's that are integers such that it is between 0 and 4 and it makes the statement true. Okay? Check to see that the set builder notation also generates the set 1, 3. Whenever you see set builder notation to describe a set, a powerful way to interpret that notation is to think of the set as being generated by a program like the for next or if then code above. So our set of all x's integers between 0 and 4, it has to be between 0 and 4 and it has to make this thing true, which the only things that work in that loop are 1 and 3. So, exploratory challenge. Next, we write code that generates a graph of a two-variable equation, y equals x times x minus 2 times x plus 2, for x in that set, and y in that set. The solution set of this equation is generated by testing each ordered pair x, y in the set. So I've got negative 2, negative 3, negative 2, 0, negative 2, 3. And then we go through negative 1, 3, negative 1, 0, negative 1, 3. And then we're going to do 0, negative 3, 0, 0, and 0, 3, etc. We're going to match up each one of these x's, with each one of these y's. Okay? And then we're going to see if a solution to the equation y equals x times x minus 2 times x plus 2. Then the graph is just the plot of solutions in the Cartesian plane. We can instruct a computer to find these points and then plot them using the following program. Let's look through this program. First, we're going to declare x and y integers. We're going to initialize a G as an empty set. And then for all x, given here, for all y, given there. If y equals the multiplication of the x values, the linear terms, then append xy to g. Okay, make it a part of the answer. Else, do not append xy to g. Next y, next x, print g, plot g. So this middle loop tests whether xy is in fact a solution to this equation. If it is, it'll append it to the set and it'll print it and then plot it. Phew! Okay, the outer loop loops through each y for x equals 2, x equals 1, x equals 0, x equals 1, x equals 2. So it'll grab a y, test every single one of the x's, and then re-loop back and grab another y and test every single one of the x's. Okay, it's quite a loop. Let's try it. So use the table below to record the decisions a computer would make when following the program instructions above. Fill in each cell with yes or no, depending on whether the ordered pair would be appended or not. Okay, x equals negative 2 has been done for you. I believe in the last slide I said it's going to grab a y and test all the x's. And that's not what it's going to do. If I look at this again, we're going to grab an x, we're going to grab an x, test all the y's, and then start over. Grab another x, test all the y's, grab another x, test all the y's, grab another x, etc. So I think I said that backwards. I apologize. So I'm grabbing x equals negative 2 and I'm testing y equals negative 3, y equals 0, and y equals 3. I'm not going to do all the math for you. If I show you, let's do two of these. We're going to do y equals -3 and y equals 0. So I have -3 equals x times x minus 2 times x plus 2. Well, this term right here gives me a 0, and if I multiply a 0 times a 0, the whole right side of the equation is 0. So that is definitely a no. And if I test 0 for the same right side, again, this gives me a 0, which wipes out everything, so I have 0 equals 0, which is why that is a yes. Okay, let me erase that. And we'll test another one. And what I'm going to do is plug in x for the right side and just see which y matches. So I've got x equals -1. So I have -1 times -1 minus 2 times -1 plus 2. -1 times -3 times 1. That gives me 3. So that's just going to be a yes right here, and a no, and a no. Try the next one, x equals 0. This one should be sort of easy. I've got 0 times 0 minus 2, 0 plus 2. Well, this 0 wipes out everything because it's multiplication. So I'm going to get a yes here, a no, and a no. X equals 1. 1 times 1 minus 2, 1 plus 2. I've got 1 times 1 minus 2 is -1 times 3 gives me a -3. And then x equals 2. 2 times 2 minus 2, 2 plus 2. Well, this center term right here gives me a 0, which knocks everything out because 0 times anything is in fact 0. All right, there we go. On the next slide, yep, what would the output be? So what would the output to the print G command be? The first one's done for us. I've got a yes there. A yes here, a yes there, and a yes there. So that would be my output. I have -2 comma 0, which is the first answer. Then I have -1 comma 3, 0 comma 0, 1 comma -3, and 2 comma 0. These would all be in parentheses because they are in fact ordered pairs. Cool. So to plot these, I would plot -2, 0, which is done for me, -1, +3, 0, 0, 1, -3, and 2, 0. There we go. I've got nice dots. So the yes answers give me a dot on the Cartesian coordinate plane. A little look into things. I'm giving you extra knowledge today. My equation was y equals x, x minus 2, x plus 2. If I multiplied this whole thing together, I would get y equals x to the third and some other stuff. This is cubic, and a cubic graph always looks with a lump up and a lump down. So it worked. It's a very nice graph. But we can't connect the dots because we tested integers, remember? So we can't connect the dots. All right, Exploratory Challenge 2. The program code in exercise 3 is a way to imagine how set builder notation generates solution sets and figures in the plane. given a function f of x equals x times x minus 2 times x minus 3 with a domain and range all real numbers, all real numbers, all real numbers, a slight modification of the program code can be used to generate the graph of the equation y equals f of x. So the set of all xy such that x is real and y equals f of x. Okay, so we're going for real numbers now, not integers. Even though the thought code below cannot be run on a computer, students can run the following thought code in their minds. The computer can't actually deal with real numbers. It can't plot every single number on the face of the planet. It can do integers, just great, but not real numbers. So a computer stepping through all numbers x from negative infinity to positive infinity on the x-axis, it's impossible. Okay, so the computers can't do that. I mean, it can get darn close. You can set up something to, I don't know, pick all real numbers to a certain decimal place, but negative infinity to infinity, it would just keep on running and running and running because there is no end to infinity, correct? All right, let me grab that computer program. Hold on. So this is the what we tested with the last exploratory question, and what we got, right? And like I said earlier, this is a cubic function. So yeah, I tested integers, but I know that my answer is going to be every number in between the dots. So that's what my graph would look like. It's pretty cool. So describe how the thought code is similar to the set builder notation. Well, we're testing all numbers x and plugging it into our function to get all numbers y. So let's see. I'm going to check xy every point from negative infinity to infinity, xy in the Cartesian plane, searching for points xy for which the equation y equals x, x minus 2, x plus 2 is true. The only difference is I'm checking every point, not just the integers between the integers listed, negative 2, 2, 0, etc. So in this one, my domain, because we're having a hard time figuring those out, is going to be all real numbers. And my range is also going to be all real numbers. All right, relative maximum for the function f occurs at the coordinate given, you see there. Substitute this point into the equation y equals x squared minus 4 to check that it's a solution. So if I graph this again, what they're saying is relative maximums are on your graph the point that's the tallest. Okay, this would be a relative minimum. We want to make sure that this coordinate actually is a relative maximum or minimum. So we're going to substitute this into the equation y equals x squared minus 4 to see that it's a solution. So relative maximum, x coordinate. All right, so we're going to substitute this point in and make sure it works. Okay. First thing I did here was change negative 2/3 root 3 into a decimal, and I get negative 1.15 approximately, and then 16/9 root 3, I get 3.08. So I'm going to plug those in with an x and a y. 3.08 equals 1.15 squared minus 4. Squared minus 4 times this does in fact give me 3.08. So it is a relative maximum. So I would plot it right there. Negative 1.15 up 3.08. A relative minimum is the same thing if we graph this again. So if I plug those into the equation y equals x, x squared minus 4, it is in fact true, and it would plot down here. This one plots up here because my graph looks like that. On what intervals is the function decreasing? This is important. You're going to get a lot of questions like this in your homework. Decreasing, if I start at negative 2/3 root 3, it decreases through the x values. That's where it always decreases, between negative 2/3 root 3. I'll highlight it. Those are decreasing. We'll do the next one in blue. Increasing would be from here and there. And if I wrote it, I would have when x is smaller than negative 2/3 root 3, or when x is bigger than positive 2/3 root 3. I could also say from negative infinity to negative 2/3 root 3, or positive 2/3 root 3 to infinity. Okay, that's hard, but really we're looking at our graph to find out where things are going up, that's increasing, and where things are going down, decreasing. We found an interval, so I find a maximum and a minimum point, and I write them out for increasing or decreasing. If you get stuck in your problem set, just let me know and we'll talk through it again. Lesson summary. Go ahead and read through it. Increasing, decreasing, important. This is also in your problem set, so you can review it. That was a long video, so we're good.